worth my time, almost. It almost makes it interesting from my perspective. All right, so let me just get the numbers. So we got 2100 volts, 1/10 of a Tesla, and it's a proton. All right, that's all I need. 2100 volts. All right, this is problem number 2, I think, from the handout. So let's just find that. This is problem number 2. Problem number 1 is straightforward, so I'm not going to waste my time on it. Problem number 2, and I'm just reducing everything to part C. Okay, problem number 3. I'm going to make problem number 3 an extension of problem number 2 because I'm going to use the same numbers. In fact, if this was an in-person class, you would have had a test questions. I would have probably skipped all the way down to B or something in order to make it interesting. All right, I would have asked you to solve this in one single try, and that would be an interesting problem to solve. All right, let's move forward. All right, let's get out of here. All right, so problem number 2. All right, the first thing I'm going to do is just, let's go with what's given. All right, so what do we know? We got something given. All right, remember, this is going to be 1/10 of a Tesla, and the voltage difference is 2100 volts. And figure out the radius of the proton beam in terms of meters. And what else? I know the charge Q, C unit charge. And I don't know if we will need this, just in case we do. I'm gonna put down the mass of a proton. It may be useful at some point. All right, that's it. So that's what's given. Okay. So the next thing I'll do is I'm gonna kind of visualize this. All right, before I solve the problem, I want to make sure that this is something that I can visualize. So let's visualize this. All right, so let's go across. Okay, visualization of it. All right, so number 1, the beam is going to accelerate through the capacitor. All right, so this is positive charge. This is going to be negative charge plate. So the positive charge is going to accelerate through the capacitor. So we'll have the proton beam, and we know something about the voltage or potential difference, which is going to be responsible for the acceleration. And then, so when the beam shoots out, it's going to have a definite speed. All right, so it's going to come out at a given predictable speed into a constant magnetic field region. All right, and I'm just going to point my magnetic field into the page. And then what's going to happen to the beam? It's going to just come in. All right, so it's got a velocity vector here. All right, so velocity, all right, is in the downward direction. So this is what the particle is going to do. It's going to go in a circular motion within this region. All right, so this is going to move in a circular motion within that region. And then the question is, what is R? R is what we're trying to figure out. R is what we're trying to figure out. All right, so how do we do this problem? R is what I need, so I'm going to directly try to figure out how we can come up with R. So what do you think we should use? Okay, so unfortunately for us, we don't have some kind of a solution manual that we can cheat from. So and the sad part of it is we have to do it the old-fashioned way, trial and error. My preference is we try, but I'm hoping that we will solve the problem at the first attempt because I need to finish up the lecture at some point. So what do you guys think that we should do? I'm thinking that we should come up with something that has R in it. This is the easiest way of doing it. All right, guys. The reason why I do stuff visually because there's something happening here, and I see what's going on. So it's circular motion. So what do you think this is? Circular motion is caused by a centripetal force. So what is the centripetal force in this case? Oh, it's the magnetic force. There you go. All right, so forget a centripetal force formula. MV squared. It's got R in it. R in it. Oh my God, it's got R in it. Shit, it's got R in it. Yeah, these are twins. All right, that's it. All right, this is. I mean, if you don't like cheating, this is faster than cheating. I mean, if you know what's going on, boom, just write down the formula. This is your starting point. All right, change the color. Change the color. All right, so it's just the magnetic force acting on it. So what we know, the magnetic force is responsible for magnetic force is the centrifugal force. The centrifugal force is the magnetic force. So here's your generic centrifugal force formula, and here's your generic, not the generic, but this is the scalar version of the magnetic force formula. All right. Before we move any further, okay, what is the angle? What is the angle between the velocity vector and the magnetic field? All right, so the velocity vector is pointing in the downward direction. The magnetic field is going into the page, so you know this is going to be 90 degrees. So this thing is 90 degrees. All right, so what that means is this entire thing is going to be 1, okay, and that's it. All right, so we got a simplified expression QVB. All right, so the next step is this equals that. This side is going to equal to that side. And so we have our mv squared divided by r, and we have QVB. All right, so we're sum for r. We'll okay, I think we can handle this. All right, so one of the v's will cancel, and sum for r. Switch those two, and we're done. mv divided by qv. Okay, cool. All right, so the next step is let's check to see if we got everything. All right, let's do this again. Just want to make sure that we got all the numbers right. I know the answer we don't, but it's good practice. All right, so let's check to see if we got our numbers right. Put this to the side. All right, so we got our B, we got our Q, so we're good. Hey, so we needed that. And oh yeah, this is the same as that, and we got everything right. Right?
This is. Now you need to get the velocity.
I'll give you 5. I'll give you 5 points for that one. Guys, if you're just doing things symbolically, it happens on the test, and all of a sudden this V becomes this V, because I actually changed the magnitude of this size, and all of a sudden this capital V became like a small v. All right, so this is your boom voltage, and this one is your speed. Okay, so that's it. Oh, it's horrible. So where did we get this from? Nathan, was it you? Okay, so where did we get the speed from? Yeah, so you kind of get your speed from the electron gun. So this life is just horrible, man. This is the reason why sometimes suicide is a good way to go. Damn, where do you get the speed from? This is I don't know. If you're completely clueless, use kinematics equations. If you're somewhat with me up to this point, I would say, damn, here's an electric field. All right, it's going to cause a force on this charge. The charge is going to get displaced in this direction. It's a conservative force, so which means that the potential energy of this charge is going to turn into kinetic energy, conservation of energy. Remember, if you don't, that's fine, not a big deal. All right, don't major in physics. All right, so what do we know? So this potential energy, U, QV, is going to turn into the kinetic energy 1/2 mv squared, and because electrostatic force is a conservative force. Okay, cool. All right, after that amazing explanation, let's move forward. So this is what I'm interested in. I'm about to do something that I didn't want to do, but let's do it anyway. All right, so what do we know? Since the mechanical energy is constant, all right, so inside the capacitor, all right, guys, this is energy. So what do we know? Which means that the initial and the final energies will be the same. The initial energy is going to be all potential energy. The final energy is going to be all kinetic. All right, so the initial energy is this. The final energy is this. After that explanation. And I'm doing something that I'm already hating because I wanted to keep that in terms of mv squared, but that's fine. All right, gotta make some sacrifices. All right, sum for v. upon solving it for V, so what do you get? It's going to be 2QV divided by M, and then put our roof on top. All right, so we end up getting an expression for V. All right, so this expression is going to go there. All right, so all right, so let's do a substitution. So I just put it in here, and then we may have to clean this up a bit. All right, M divided by net charge times this strength of the magnetic field. So we have 2Q. What's up?
Well, since that, I'm just curious, why are we still keeping the same equation, that MV over QV? Wouldn't that still be incorrect because we assumed earlier that, voltage and velocity were the same V, so we canceled them out? Wouldn't we have to reformat that equation first?
Okay, who's talking? Lucas?
Yes.
Okay, Lucas, all right, let's get back to what you were saying because, okay, you lost me a little bit. Okay, so tell me which, okay.
MV squared over R is equal to QVB. Since that, oh, never mind, I'm sorry.
Okay, are we here?
Yes, I understand. I am incorrect.
No, you're fine. Okay, I see what you're saying. Okay, so I wanted to keep it here as is because I knew that I was going to use the kinetic energy formula, but at the same time, we got V on both sides, so it makes it really complicated. So I decided that this is the way I want to go. Okay, so this is good at this point, I'm assuming. And because, why am I assuming that this is good? I'm assuming that this is good because I think we got everything that we need at this point. I don't like the format, but I think we got everything that we need. I can simplify this further, which I probably will. All right, so M is here, Q is here, B is here. And we also got the voltage. Cool, I'm good, okay. I'm about to do something. I'm afraid to do it because some of you guys get confused so easily, especially the community college students. All right, guys. Okay, I don't like saying terms. In prison, out of prison, in prison, out of prison. Okay, so it just messes up. So we gotta do some cancellations. All right, so I want to finish this up. All right, so here's what I'm gonna do. I'm going to show you something. I want to get rid of this. So I'm gonna square everything, and then I will do cancellations and take the square root. Got it? So I will square everything, and then I will take the square root. And then just before I take the square root, I'm just gonna cancel the like terms. That's what I want to do. All right, so whoop, 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 whoop. Everything gets squared. And then I'm gonna do, and then I will take the square root of everything. All right, so I'll just get rid of the like terms. These two will cancel, these two cancel. I think that's fine. All right, boom, boom. All right, and do we have any other cancellations? I don't see any other cancellations. Okay. All right, so we got 2 M, and we have the voltage. Then in the denominator we will have Q, and then this remains as a square. All right, so that's gonna be a jailbreak for that one. All right, that's it. Okay, so now we got a clean equation. So, all right, well, lecture 20 materials. It's not open. It should have that solution. Okay, so the problem number 2 is the one that we just did. All right, I end up doing everything in one single step. All right, if you break it down into 3 steps, obviously this is what you end up getting. So the solution is going to be 0.0066 meters. That's what you end up. All right, so that's where the solution is. All right, so here's a question for you before I let you guys go. Part B of the question. All right, forget the mathematics. I'm interested in finding change in the proton's kinetic energy.
It's going to be 0.
It's going to be 0 because?
Because the force is always perpendicular to the displacement.
All right, so I'll give you 5 points on that one. I kind of like that explanation. I'm looking for something a little bit more direct. All right, guys, for you to be able to transfer energy, the force needs to have a component on the direction of motion, which means that the force has to be responsible for that motion, right? So when the force is 90 degrees to motion, force does not have a component along the direction of motion, so which means that the force does not impart energy to the particle. So there's no change in kinetic energy. Kinetic energy in circular motion is going to remain constant.